DI504, Foundations of Deep Learning, and this is week 6. We're going to talk about deep training, but before the lecture, let me give you some information about some administrative stuff. To begin with, the midterm. Most of you have been asking questions before the lecture. Well, the midterm is next week. Next week today. So it will be on Wednesday, but it won't be in the lecture hours. It's going to be in the, it will start at 8 o'clock and it will take 3 hours. I guess 3 hours will be okay, but I'm going to check again this week. Maybe I'll make it 3.5 hours, don't know. How it's going to be is, it will be an online assignment at ODTÜ class. You're going to download the PDF. You're going to solve the questions on a white paper. And you're going to upload it before the deadline, the deadline hour. I don't know, it's like 11 p.m. or I don't know. I'm going to decide it. I'm going to email it to you. So what I'm kindly asking you is to prepare yourselves for next week's midterm, which will be in the evening. Okay. So that evening you'll need some time for yourselves. That day you won't have any lectures. I mean, I've tried it, it doesn't work. So it will be the midterm. So you have questions about the midterm. I know that. It will be about the things that we're covering in class. So nothing that we don't cover in class will be included. Don't worry about it, because this is this is an interdisciplinary course. It is related to many things. So what I recommend is it will be an open source exam. So feel free to check any sources. I mean, not including anybody else, but inorganic sources from the internet. You will need to make some calculations at some point. So just like you use a calculator in your midterms, you will need to use, I don't know, MATLAB or Python. But you will have, they will be simple calculations. So don't worry about that. And the calculations will not be just calculations. The calculations you are going to do will be, the purpose of those calculations will be to understand a part of the question. So I'm going to ask you a question. There will be some numbers maybe for some of them, in some of the questions. You're going to calculate this, you'll do a simple calculation, which will lead to a, conclusion. It made this, so it must be this phenomenon, kind of, which we covered in class, related to training stuff, related to actuation functions, and we're going to cover many things today as well. So if you study the video lectures, it will be okay for you. That's it. I mean, next week, Wednesday evening, be ready for the midterm. Other than that, you have started your labs. Thanks to our TA, Ozan. In labs, you have covered a simple network, and actually you're given an assignment for training a simple network. And we are going to cover those concepts today. So today's lecture will prepare you for that assignment as well, in a way. So with that assignment and with today's lecture, you'll be ready for the midterm, but more importantly, I believe that you'll be completing the first half of this course, which is actually the fundamental introductory level to this course. I mean, you've come to a point where you know after this lecture, you're going to know the fundamental concepts. How to train a network, what is a network, why it's a computational graph, backpropagation, gradient descent, what is training, how can I train, how can I solve problems. So this is a very fundamental point, in my opinion, because after this point, everything will be accumulated, will be put on top of this fundamental base. Okay? Okay, so this was the administrative stuff. And one more thing. I've spoken to Ozan, or teaching assistant, TA. Ozan is doing his studies on NLP stuff. NLP is natural language processing. And in NLP, we're going to talk about this. I'm going to make an introduction to those concepts after the midterm. And in NLP, the feature extraction is kind of different. Up to now, we have covered convolutional neural networks and feature extraction logic with respect to convolutional neural networks. And that is related to more like signals, not a language. Okay? And Ozan told me that he did talk about these features of NLP, which are called word embeddings. And it confused some of you. Don't worry about it, guys. I mean, we are going to get there. And you're not responsible for any word embeddings, for any NLP features in the midterm. And you will be responsible, you will be responsible for those topics when we learn them in the following weeks. So if any of you are confused with those concepts, don't worry about them. I mean, Ozan loves the study he's doing, so he wanted to mention a little bit about it. So I don't want it to frighten you, okay? So we are going to get there. Okay, so that was the administrative stuff. Let me begin. This is important, okay? Deep training. Well, at this point, we know how to construct a deep learning model and what it is, what it mathematically represents, okay? And we kind of know how to practically train it, but we don't know the details of the training. Today, it is what we are going to learn, okay? Today, we are going to learn what it's all about, this training and learning. It's going to be, we are going to be putting on top of what you've been doing in your labs. Let me start with backpropagation. The idea of backpropagation. I repeat, backpropagation is an efficient way of implementing the gradient descent algorithm on computational graphs. Look, we have an optimization algorithm, the gradient descent, which is a plain algorithm. There are versions of it, which we are going to talk about today. It is, you update your weights according to your derivative of the loss with respect to those parameters, okay? I'm going to show you the formula. You can apply it to any analytical function that you can take the derivative of, okay? But how to apply it to computational graphs? That algorithm is called backpropagation. Backpropagation is how you apply gradient descent to computational graphs. It is important for us because all neural networks are computational graphs, okay? Things that you already know, I know, but we have to go over these. These are very important. So the pseudocode for the backpropagation algorithm is actually very simple. There are two steps, the forward step and the backward step. Let's go over the forward step and the backward step, guys. So the forward step is actually, you have an input. Actually, in gradient descent, you have an input. In stochastic gradient descent, which is a version of gradient descent, you have a group of inputs, which we call the mini batches. In your labs, in your practical sessions, you have seen this. We don't feed a single data to the network to be trained. We feed them by groups, for example, 32 samples together. I don't know what your input is. It could be an image, it could be a sound, it could be something else, it could be language, whatever your model is. It could be a vision model, it could be an NLP model, doesn't matter. We have a bunch of inputs, which I'm going to be always calling mini batches. So batch is like a group of things, batch. Mini batch is mini pieces from your training set. Mini batch, that's the word used in the literature. So we feed it to the model. This is the model, guys. This is what we have here. So let me get my pen. This is the model, guys, okay? This is the model. So there are two boxes in the model to give you that idea of a computational graph, because in the end, all deep neural networks will be layered architectures. There will be activations, okay? So when you're doing the forward pass, what you're doing is you feed an input, mini batch of inputs. So at each layer, this is layer 1, this is layer 2, you are getting some activations, activations 1, activations 2. And actually, the activations of the final layer is the output, okay? You keep these activations in mind. You don't lose these activations, okay? So when you're doing the forward pass, I mean, if your aim was to calculate the output, for example, for a forward pass only, you don't have to keep the actuations of the hidden layers or the intermediate layers, right? Because when you have this actuation value, you feed it to the next layer, and you get the output of the next layer, and you won't need this. However, in backpropagation, in the first step, in the forward pass, we keep these. I mean, I say we keep these. Your algorithm or your library, PyTorch, will automatically do that for you, but that's how it's done. So I'm going to say we keep these as the people who are implementing the backpropagation algorithm. So we will not forget the activations. This is very important. Then we have an output. Since the method we are covering today is actually a supervised learning model, we have a ground truth, okay? And that ground truth is also called the desired output. So what this input should have given us is actually the desired input. And the loss function is kind of a distance between that desired output to the actuation of the final layer, okay? Because we have started with some weights which are not true. That's the purpose of the training. That's the purpose of the backpropagation. We are trying to find those weights, okay? In the end, there will be an error between the actual output and the desired output. And we call that loss, okay? We take the derivative of the loss. At this point, we take the derivative of the loss with respect to what? With respect to itself, guys. It's funny, I mean, something taking derivative with respect to itself is one. So we start backpropagating the derivative starting with 1, okay? Then what we do is, so this is actuations 1 and actuation 2. We backpropagate the derivatives, because what we are trying to find is we have the weights of this layer, weights of this layer. What we need to find is the partial derivative of the loss with respect to these parameters. Because if you can find this, you can calculate how you can update these weights. Remember, this is the blind guy walking. And this is the gradient descent algorithm. And while you're doing this, I'm going to get into more mathematical details of it as well. You need the actuation functions that you have calculated in the forward pass. So simply put, the backpropagation algorithm pseudocode is, you do the forward pass, you keep the activations, you calculate the loss, then you backpropagate the partial derivative of the loss in the computational graph to find the derivative of the loss with respect to the parameters at each layer separately in a reverse order. Okay, first this guy, then this guy. When you find this, because when you backpropagate the errors and find the partial derivatives with respect to the chain rule, remember how we have calculated the backpropagated errors in a computational graph in the previous weeks. If you don't remember, go over them. It is important it is important that you understand how that backpropagation works. Okay, so you calculate these. What am I going to do with these? What am I going to do with these is called actually the gradient descent. Let me get to the next slide. So before I get to what I'm going to do with it, it is here. It's going to be here. I'm jumping, but I'm going to jump back. Don't worry, I'm going to show you something. Because it was the gradient descent, because this is the partial derivative of the loss with respect to the parameters. I indicate the parameters as theta here, but it could be indicated as omega or W, it doesn't matter. I apply this at every layer. That was the purpose of it. Before getting into more mathematical, into more intricate mathematical details of it, let me talk about how it is implemented in a deep learning framework. For example, PyTorch, because that's the one we are focusing on this course, but there are many. TensorFlow is another one, Keras is another one. MATLAB has its own, and there are older versions, including C, like Caffe. We don't use it anymore, it's dead. So somebody in the deep learning framework, something, should be able to calculate these partial derivatives along the graph architecture automatically. That thing in PyTorch is called autograph. If you are going to train something in PyTorch, you will need to understand autograph properly, guys. I mean, you are not at a point that you can understand it deeply now. You are doing a gentle introduction to training and using PyTorch and autograph. But that is the architecture we find in PyTorch. So autograph in PyTorch is a reverse automatic differentiation system. That framework, that sub-framework of PyTorch is used to implement the backpropagation in the computation graphs. So what it does is, it does the forward pass and the backward pass. And in the forward pass, I said we keep the activations. Autograph does it for us. And the backward pass, it automatically calculates the derivatives. So at this point, autograph will need the ability to calculate the derivative of a layer analytically so that it could find the partial derivatives and backpropagate them, right? Because in here, when you're backpropagating the derivative of the loss, you need to know the derivative of this layer, right? Let me remind you that. This is important. So derivative of the loss with respect to activation 2, because we have activation 2 here, and derivative of the loss with respect to activation 1 here. And what I need to find is the derivative of the loss with respect to the parameters of this layer. Let's say this is layer 2, and the parameters of the layer 2 are represented in a vector called W2. So I would write this function as derivative of the loss with respect to omega 2 would be something like derivative of the loss of A2, this guy, times derivative of A2 with respect to omega 2. So A2 is the output of this guy, okay? So this guy is actually like a function. Let me write that function. It was a function of A1, the input, and omega. So let me not use this thing here. This is not a good idea. Let me say, if it's a function, let me say F, activation function of omega, giving me A2, right? So if I want to find the derivative of A2 with respect to W2, I should take the derivative of this function. So derivative of F A1 omega 1 with respect to, sorry, omega 2. So that's these are the same things, right? So this is what I need to find. So autograph, when it's doing its job, if this is a black box, and if that black box is a layer, needs to be able to calculate the partial derivatives of this function. It's a black box function with respect to omega 2. Okay? So for autograph, the PyTorch, to be able to do this, autograph will need to create a graph representation of its own. And in that graph, each node will be a specific type of data structure where PyTorch is able to calculate the analytical gradient. Okay, I hope you can follow. So actually, that's something PyTorch can do. What PyTorch does is, when you write a model like this, because you have done this, you have created a simple model in your lab. Remember? This is a more complex one. So it's a matrix multiplier layer. It's matrix multiplier is a weight multiplication layer. It doesn't have to be like that. You can use a linear layer, which is also matrix multiplication plus bias, remember? But in a computational graph, it doesn't matter. In a computational graph, it could be a fully connected layer, or it could be something simple like addition. Doesn't matter. What PyTorch can do is, when you create a forward model like this, the autograph, that function, automatically creates the graph for you. And when it's creating that graph, PyTorch asks you to use classes, data structures, which it can recognize so that it can calculate the gradients. So what you do is you write that model, that forward model. When you're writing that forward model, you put some functions, layers, layer or function, the same thing in category, but in deep learning you use layers. It creates that graph automatically, and when it's creating that graph, it checks if it can take the gradient off. If it can do it, what AutoGrad says is, okay, I know this graph, I know the analytical gradients of every node in this graph, so I can apply back propagation. That's how AutoGrad works. Okay, so what you have done in your labs when you trained that simple model was, you created that graph. AutoGrad recognized that graph, and when you started to train it, which was the back propagation, remember, calculate the forward ones, then back propagate the gradients. AutoGrad was ready to do it because it recognized that graph. That's how you implement it in PyTorch. But the thing is, it is not much different in other frameworks. The nice thing is, AutoGrad creates it on the fly, so that as long as you give the data structures, the nodes that PyTorch can recognize, AutoGrad can recognize, take the derivative of, there is no limit in architecture you can create. That's why this PyTorch and TensorFlow are so powerful. You can create any type of architecture you need. And in the last 5 years, there has been many new architectures, like from YOLO to other, I don't know, transformers. And they have been created, because people had this flexibility of these frameworks and algorithms. And you can do it as well. You can create an algorithm, an architecture, which is a computational graph. And in PyTorch AutoGrad, in TensorFlow, another mechanism will automatically apply the backpropagation. So that's it, actually. That's I hope that it's a revelation for you, because this is how it is done in the codes. Everything you learn theoretically is how it's implemented in code. So I'm going to be showing you a simpler architecture. For example, you create a class. You know what a class is. I mean, if you've seen a little piece of object-oriented programming, you can create a class in Python. You can create a class in any language, but it is Python. So these are the properties, how you initialize it. So in the initialization step, we designate the parameters of the network. So if I look at, the first one is a convolutional layer with some number of filters and some number of filter sizes. Then a pooling layer, a max pool layer, 2 by 2. Then another convolutional layer, then a fully connected layer, then a fully connected layer, then a fully connected layer. As long as the parameters hold, for example, the output of the fully connected layer should be the same as the input of the next fully connected layer, so that the network can, connect. If it is not, PyTorch will throw an exception, an error to you. Okay, as long as you can do it, at the forward part, you design the graph, because which layer is connected to which layer? You don't say that. You just create these layers independently in the space. There are no connections in between. You didn't create the edges, the directed edges yet. They are just nodes. When you put the edges, it will become a graph. And it is where you make this graph, this forward function, which is inherited function of this NN module. This is, so you create a class net, which will be inherited from this superclass, inheritance property in object-oriented programming. You know this. So you create the graph here. You create the connections. And AutoGrad checks the forward function and checks, do I know the nodes? Do I recognize the connections? Okay, there's the graph. I can take the derivative of. And you don't have to create a backward function. It will automatically do it for you. But if you have a specific node that this guy does not recognize, you will need to write a backward function for that node, so that AutoGrad will know how to take the partial derivative during backpropagation although it does not recognize that class. So that's the flexibility. You can add any type of function to the graph, even though PyTorch doesn't have it. If you can provide the analytical gradient and the forward function, it will do the job for you. This is PyTorch, but TensorFlow and Keras, they all have this capability. This is how it's implemented. I hope these explanations were somehow valuable to you after the labs, because I just waited for you to finish your first lab to get to this point. Okay, any questions about how the backpropagation is implemented in PyTorch? I mean, it's an important discussion, so feel free to ask any questions in the classroom.
I have a question.
Please.
At the end of this course, at the end of this code, are we obtaining only one fully connected layer?
Well, at the end of this class net, you mean?
Mm-hmm.
Well, actually, we have many layers here. This cone 1 is a layer. Pool is a layer. Cone 2 is a layer. And FC1, 2, 3 are all layers. Your friend is asking, did we obtain just one fully connected layer after this code is implemented? Actually, we have created a large architecture with many layers, including 3 fully connected layers, because linear is a PyTorch function class which creates fully connected layers. So these are here, actually I have created those layers, did not connect them. And at forward part, I connect them and I create the graph. This is a fully PyTorch AutoGrad compatible computational graph which you can train. Is that an answer to your question, Ilkim? I guess because you were kind of confused.
Yes.
Okay,
Thank you.
I hope it's an answer to your question. Okay, okay. Okay, so that's it. That's how you do it. With this knowledge, there is nothing you cannot do. I mean, you can create any type of architecture. I mean, it might be frightening for you right now, but that's the fundamental of it. When you get the experience, you will be able to create anything you want, any architecture. I mean, will you be able to train it? I don't know, depending on the architecture, maybe the gradients will not flow or it will have some difficulties in training. I don't know, but it is a well-defined architecture when you do it this way. Okay. Okay, any other questions from classroom?
Hocam ben bir şey soracaktım.
Please.
What is your choice of PyTorch or Keras TensorFlow? What do you think about this?
In this course, we are using PyTorch. You might have already realized, but are you asking me personally?
Yes.
This is a difficult question. I don't recommend Keras to start with, because Keras is like MATLAB, and you cannot get into the details of the algorithms. So if you want to do toy examples, okay, use Keras or MATLAB. But if you're into deep learning, I mean, I think you are all into deep learning because you are taking a introductory level deep learning course. I think if you're going to be following an academic path, it is PyTorch. If you're going to be following an industrial path, it is TensorFlow. But these are very, controversial subjects. People will have different opinions. He's asking which framework to use.
So we can use the both of them in our project.
Well, you can use it's you can, but I mean, your labs are in PyTorch. You know that. So I think that you have some experience on TensorFlow as well. That's why you want.
No, I don't have it, because I see that the PyTorch is a little bit complicated than the Keras and TensorFlow.
Well, it is not more complicated than TensorFlow. TensorFlow is also complicated, but it is complicated than Keras. I strongly recommend not to use, for you guys not to use Keras, because Keras is, you won't be able to control anything in Keras. So use PyTorch for this course. But if TensorFlow, it's okay, but TensorFlow is still, you will have these problems.
Thank you, hocam.
Okay.
Can I also ask the question?
Please.
At the end of the forward part,
function.
Yes, we don't use any activation function because of the choice of the loss function.
Well, your friend is asking why there is no activation function in the forward part. Well, this is an advanced question. Your friend is asking, actually, we were talking about how to construct a computational graph and how AutoGrad automatically understand the computational graph architecture. So your question is more like, what kind of a network is this? What is it good for? I think it doesn't provide anything to us. And you're right, but it's a toy example. So most probably it's not going to work because there is no...
Every time I'm confused about it, therefore
Yes.
I want to ask.
Because your friend is saying there's no activation functions here. And if there are no activation functions, there's no nonlinearity, then it's just a simple, I don't know, linear system of equations. But actually, because of the max pool function, which is nonlinear in nature, it is not, but it's a stupid network. Yes, it's a stupid network. It's just a toy network. Not to confuse you, because I'll start to talk about the activation functions in the next slide. That's why I didn't want to put them here. Okay? But never forget that the convolutional block, just like in AlexNet, or just like in UNet we have seen the previous week, you will need a weight multiplication layer plus an activation layer. Right? We have seen the UNet previous week. Yes, please. Another second question then.
No, thank you.
Okay. Any other questions? Guys, this is the heart of it. I mean, this is the deepest level you will get in the introductory level course. Okay? I mean, there are deeper things you can do with AI and deep learning, but at the introductory level, this is the deepest we get. So don't get frightened. I was trying to prepare you for this point. Maybe you haven't understood it 100% right now, but you will. Keep the things that I told you in mind and practice in your code. And most importantly, what I recommend you is to get a proper understanding of deep learning and training. You will be constructing that backpropagation loop in your PyTorch codes, in your projects and the labs. Debug that session. Debug it. So line by line debug it. What happens? So it calculates and calculates and calculates. It is very important. When you understand this, actually, you can build anything on top of it. Your PhD thesis, your papers, and whatever. That's kind of the heart of it. That's why I was trying to prepare you up to this point. Okay, so I continue if there are no questions. Okay, so the previous weeks, the last 2 weeks actually, the last 2 previous weeks, we have started with AlexNet. Then we have seen different layers that we find in deep learning architectures. Different type of convolutional layers, different type of max pooling layers, input layers, and etc. We've talked about the activation layers. I'm going to visit them again, revisit them, because the nature of the activation function is actually very important when we are applying the backpropagation algorithm, because it decides the analytical gradients, because it's where the nonlinearity happens. And where the nonlinearity happens, the derivatives become complicated, right? Because if everything is linear, derivatives are simply multiplications. But depending on the nature of the activation function, the derivatives can all even get dead. They can die, because these activation functions have 0 derivatives at some point. I mean, what is the reason for that? I'm going to delve into this stuff today, right now. So we've talked about different activation functions. We have seen that the ReLU, the famous one, was used in AlexNet. It was kind of a revolution because this was very fast. Its derivative was very simple. So we could use it. But traditionally, in deep neural networks, we also said that these regularized activation functions were used, like the sigmoid or 10H. By regularized, I mean the output is regularized. The output is bounded between -1 and +1 in 10H, the hyperbolic tangent. And in sigmoid, it is between 0 and 1, as you can see, 0 and 1. The output is bounded between 0 and 1. But the more important thing is, if you just look at it from the perspective of backpropagation, is the derivatives of these activation functions. Here in this figure, we have their derivatives. So as you can see, if you check it, apart from LU and ReLU, and actually these linear units, the rectified linear units, this is actually leaky ReLU, max out, or LU. These are some versions of ReLU. So this is like, we can just classify these guys, these four guys, let me get my pen, as ReLU variants. As ReLU variants. These are ReLU variants. These guys, apart from these guys, actuation functions, the traditional ones, have derivatives, have non-zero derivatives in a bounded region. For example, look at sigmoid. The sigmoid derivative in this figure is black. Sorry, it's blue. Is that blue? Yes. So this guy. It is mostly zero after some negative point and after some positive point. So it is non-zero for a limited region. What kind of an effect does it do? What kind of an effect does it do? To understand its effect, we should remember the backpropagation. Imagine this is a layer, guys, because this looks like a convolutional block or a fully connected block. Let's see, this is a fully connected block. Okay, this is a fully connected block. Okay, input comes here and output goes out. Okay, so how you calculate this? You have an input. You have the input vector multiplied with weights. Okay, there's x0 as well. You add the bias. You have a value. You insert that value to your activation function, which is f, as you can see, which is f. Let's say it's a sigmoid. Let's say f is sigmoid. Okay. This is the forward pass. There is nothing strange about the forward pass. Let's get back to, or let's jump into the backward pass. In the backward pass, if we confine the backward operation to this layer only, what will happen? There could be layers in front of this layer or backward at the back of this layer, but what backpropagation will be doing specifically to this layer is you will have a derivative of the loss with respect to, let's say these are the activations of layer I. Okay, activation layer I. So the loss, the derivative of the loss with respect to this output here will be backpropagated to this point. And you will be backpropagating it, let's say xi, the input to the layer I, because this is layer I, okay? So you will be backpropagating the derivative of the loss with respect to xi. So what you will need is to backpropagate it, and while you're doing that, you will need to update these weights. So I'm going to be putting this simply like this. So this function here, because that's a fully connected layer. So let me just continue writing it here. I'm going to write the same function. Loss with respect to partial derivative of xi will be partial derivative of the loss with respect to ai times, very simply, partial derivative of ai with respect to xi, right? So these guys will cancel and I will have this. Simple, right? So I have this here. I need this here. I'm going to be calculating this. Okay? So I need to calculate this. How I can calculate that? Let me just delete some part of it. Let me delete some part of it. Let's not delete this. Okay, so let me get a pen. So actually, since ai is sigmoid function given the summation omega xi plus b, right? I'm taking the derivative of this guy. When I'm taking the derivative of this guy, I'm taking the derivative of with respect to xi, right? So if I take the derivative of it with respect to xi, if you know the rules of derivation, it is simply, so derivative of xi will be the derivative of this guy at this value, sorry, at this value, derivative of this guy at this value times the derivative of the inside of the function, right? What is the derivative of the inside of the function with respect to xi? It is something like omega I, right? Simple. Now, I need to backpropagate this gradient backwards. So I need this value because I have this value, I need this value. I know the weights at that point, so this is not something to calculate for me. I need to calculate the derivative of this function, which is the sigmoid function in my case, with this value. And this value is actually the value given the activations at that point. I know those activations because I calculated them in the forward pass. I calculate them. For example, when I calculate this, the value is minus 20, I'm sorry. What is the derivative of the sigmoid function when the input is minus 20? Well, when the input is minus 20, it is something like a straight line. So it is very close to 0, guys. If it is very close to 0, this will be 0. This will be 0. This will be 0. And this will be 0. As you see, the gradient that is backpropagated is dead. It died. That's the problem with the conventional, traditional activation functions. Since they have 0 gradients for most inputs, during the gradient descent algorithm, the derivatives die. If you do not have any gradients backpropagating towards the inner layers after this point, you won't learn anything. Because actually that derivative of the loss function that you backpropagate is like the electrical signal that updates your weights. That's the algorithm. And when it dies, you lose everything. That's why ReLU is good. As long as the inputs are positive, its gradient is never dead. It's 1. It's a simple 1. So as long as this value, if this was a ReLU, and if this was not negative, positive, a gradient would pass, and it will be 1. So it will be, this will be 1. It will be passing the gradient backwards. So the signal will be passing because that is the learning signal. That's the feedback signal that keeps your network learning. That's why ReLU is better than sigmoid when you have deep layers. However, remember, what if this is negative? For a ReLU, it is still, the derivative is still 0. So in ReLU, you have this gradient dying problem as well. And actually, it's called the dying ReLU problem, which we are going to be seeing in a couple of slides. So, this was a simple demonstration of how gradients pass and how activation functions manipulates that gradient pass. Okay? So for example, what about sigmoid? That was what we were working on in the previous slide. Its squashes numbers, it's bounded between 0 and 1. It was historically popular because in the previous artificial neural networks, in the traditional ones, people thought that we need to regularize the outputs, but that's not the case actually. We need to regularize the gradients. That's why we need an activation function where the gradient is not dead for most of the range. So this was what we have done. What we have done in more simple terms. A gradient is coming. What we need to find the gradient with respect to, we need to backpropagate the gradient. So we calculate the output with respect to x. So when you calculate with respect to x, depending on the value of the input, this gradient might get 0. And saturated neurons, which means the inputs are either negative absolute values or positive absolute values. These regions are called the saturated regions of sigmoid. The neurons kill the gradients. That's a big problem for sigmoid. Okay? But sigmoid has more problems. I'm going to be talking about them. This is just one of them. Okay? Another important problem of sigmoid is the output it provides is not zero-centered. It's between 0 and 1, remember? 0 and 1 value will automatically create gradient, output values between 0 and 1. So imagine you feed batches here. You have some, you have some input values here. You have some input values. You have some input values. At the output, your outputs will be, there's a mini batch of inputs there. There's an input, there's another input. So in a mini batch, you feed many inputs all together. The outputs will be distributed between 0 and 1. Actually, the fact that this distribution is between 0 and 1, the fact that it is not zero-centered, affects the optimization process. This is a bit complicated, which I'm not going to delve into the details of it, but in a backpropagation algorithm, if the outputs are all positive, because of the operations you do in the gradient, backward gradient, the optimization directions are affected, because the optimization directions are the blind guy trying to find its way. It is like, it has an effect of similar to blind guy always trying to move in a direction, although he has to go in the backward direction, kind of. I'm not going to go into the details of the mathematics of it because it's not necessary at this level. But the fact that the sigmoid is not zero-centered affects the optimization process. Okay? Something you should know. That's why we don't use it. And another thing that we should be saying about the sigmoid function is it's computationally expensive because you calculate an exponential, you calculate division, exponential. These are things that you don't want to do in your embedded systems. Actually, exponential is easier to calculate compared to division. If you have ever taken a, I don't know, a computer architecture course or a microprocessors course, division is the worst. Square root is like devil. Exponentially, you can do it in Taylor expansions, but still computationally very expensive compared to ReLU because it's no computation, it's just if and else. So we don't use them. Okay? What about 10H? It is similar to sigmoid, but it's similar to sigmoid that it's bounded within a region and it's saturated, which means the derivative of the 10H, just like sigmoid, will be 0 for these saturated values, which will create the gradient that we encounter, which is something bad because in a deep neural network, if your gradients die at some layer, the layers behind it will not be trained because the derivative of the loss will not be backpropagated to the layers behind it, so that the weights of that layer will not be updated. However, it's not zero-centered, so it's better. That's why for most of the artificial neural networks with limited layers, 1 or 2 layers, so the first artificial neural networks of 1-2 layers, usually have 10H because it's easier to train. Because in 1 or 2 layers, you don't encounter this gradient that's much, and you can train your system. Okay. And we'll talk about ReLU and we'll talk about dead ReLU in the next hour. Any questions up to now? I think it was a bit heavy, but you were ready for it. Any questions? Please. Mm-hmm. your friend is talking about a practice specific to 10H or sigmoid. Can you please make it more specific? I didn't understand. What do they do to sigmoid? Multiplying with 0.7, you said? Okay. There are versions of 10H where they don't let 10H saturated so that your gradients do not get dead. Yes, there are things you can do with it and it will affect your training, but still you have the problem of computation. Well, good question. Well, in convolutional neural networks, they are not. In recurrent neural networks, like in designs like LSTM, they are, because you are going to delve into LSTM in the following weeks. The fact that your friend is asking, okay, why we see 10H, why see 10H in some architectures still, why there's a need for 10H. So, because there are certain architectures like LSTM. LSTM is a type of recurrent neural network design, which we are going to be talking about in the following weeks. It is specifically designed with regulated outputs. The only advantage of 10H and sigmoid with respect to ReLU, in my opinion, is their outputs are regulated. Because with ReLU, depending on the input, your output may explode. Imagine you have weights larger than 1, they explode. In a deep neural network, they will just explode, reach to infinity. When they reach to infinity, it becomes incomputable. That's why, for that matter, they being regulated, they having regulated outputs is an advantage, and it's being used in some architectural designs like LSTM. I hope it's an answer. That's why it's not there. But other than LSTM, if you ask me, are there any, conventional usage of 10H? Not much. It's kind of dead if it was not for the LSTM. And actually, transformers are taking over LSTMs. They haven't taken over LSTMs entirely, but maybe someday we will not be using any 10H. And transformers and LSTMs are actually beyond the scope of this course. I'm going to be teaching partially some LSTMs, but we have another course, sequence models in multimedia. We talk about them there a lot. So we are just stepping a little bit out of the context of the course, but still, I think it's an answer to your question. Their ability to regulate output. Any questions from the audience in Zoom or classroom?